Math 2414, Series, Video 8, Harmonic Series. I invite you to research harmonic series and see why they are called harmonic series. I believe it has to do with sound waves, but don't quote me on that. I would have to look it up myself. Excuse me. I am no physicist, as I've announced many times. What is a harmonic series? Well, before we start out with what a harmonic series is, we need to define what a harmonic sequence is. Actually, a pretty easy definition. I can get this ready to highlight. A harmonic sequence is a sequence whose reciprocals form an arithmetic sequence. Recall that an arithmetic sequence is a sequence where the difference in consecutive terms is constant. So, for example, following is an arithmetic sequence. Start with any number we want, like for example 7, and add or subtract any number we want. Let's just say we add 5. If we add 5, we would get 12. If we add 5 again, we get 17. If we add 5 again, we would get 22. If we add 5 again, we would get 27. And in general, the nth term would be 5n plus 2. Put in n equals 1, you get 7. Put in n equals 2, you get 12. And if you're wondering how I got that so quickly, then go back and watch the video on arithmetic sequences from the previous series of videos. But anyway, yeah, that's an example of an arithmetic sequence. And so a harmonic sequence, the reciprocals, 7, 12, 17, 1/22, 1/27. And so accordingly, we could write the nth term of that harmonic series as 1 over 5n plus 2. So that's all a harmonic sequence is. Sequence whose reciprocals have constant difference between consecutive terms, aka a sequence whose reciprocals form an arithmetic sequence. Harmonic series is the sum of a harmonic sequence. So a harmonic series is any series of the form, the sum, the sum, we'll just start it at sum from n equals 0. We'll start it at 0 or 1, it doesn't matter. Infinity of 1 over something like an plus b. 1 second, folks, I'm going to see why this dog is yapping away. All right, doggy crisis averted. Okay, so where were we? Excuse me. Sorry about that. We were defining a harmonic series as the sum of a harmonic sequence. So it's a sum that looks like that. And I don't like that being parked right there, so I'm just going to erase it and move it over to the side. Well, there goes all that. Do it. Highlight harmonic series. That's what we're defining. And let's write it over here. The sum equals, we'll say 1 to infinity, 1 over an plus b. Of course, this is assuming that the argument is defined for all the values that n can assume. In other words, this is assuming the denominator is never 0. All right. So, oh, by the way, often you will hear something referred to as the harmonic series, as opposed to a harmonic series. The harmonic series, sum from n equals 1 to infinity, 1 over n. In other words, it's the sum of the reciprocals of the positive integers. 1, 1/2, 1/3, etc. That is considered the harmonic series, but it's actually one of a category of series. Any series sequence is the reciprocal of an arithmetic sequence. All right, so what about these harmonic series? Well, the big question with any series is, does it converge? Or if it does, when does it converge and when does it not converge? So what do you think? For example, if we took that bottom series, if we took 1 plus 1/2 1/4, plus 1/3, plus 1/4, forever, do you think it would converge? Or do you think it would diverge to infinity? Let's actually look for some evidence. I had planned on using Desmos earlier in one of the videos, but I had not. So let's go there. Desmos. Well, we'll just open up. All right. So how can we come up with a value for this? Well, first let's define a function. Battery is running low. Okay. In a second. F of x equals a sum. Sum. Functions. Miscellaneous sum. Start at 1. We can't really go to infinity, but we're going to put x as the upper limit and just add 1 over n. Don't worry about the graph. Desmos is doing some things, but I can turn this into a table. And we can just start with 1, 2, trying to delete these rows. 4, 5, 6, 7. I can just hit enter over and over. Yes. All right. So what we've got this thing doing is we've defined a function where the input of the function is the upper limit of the harmonic series. And we're looking at a table of values as the upper limit increases. And I want you to notice, let's see if I can zoom in. Here, but that's okay. And I want you to notice the outputs, which represent the sum, the partial sums of the harmonic series. 1, 1.5, 1.823, 2.0823, getting larger, but it looks like they're slowing down. But are they? We're at 47 terms, we're at 4.437. We're at 80 terms, 85 terms, we hit 5. 127 terms, and it seems to be slowing down. We're only at 5.425. Like 300 terms. Okay, we've hit 6. All right, so I've made this table, this ridiculously long table of values that represent partial sums of the harmonic series. And the one we stopped at was the 321st partial sum. But I can manually type whatever upper limit I want. For example, let's say I want to take 1,000 partial sum. We're at 7. 10,000 partial sum. We're up to 9.78. 100,000 partial sum. We're at 12. 1 million partial sum. Okay, we're not even to 15 yet. 10 million. 100 million. 1 billionth partial sum. We're almost to 19. So, oh, it's at 21 now. I guess it had to calculate it. So maybe it's not converging, because it seems like we can make the sum larger and larger by just adding more and more. And I may be breaking the limits of Desmos by asking it to calculate the sum 10 billion partial sum there so far. And I know Desmos has its limitations, and I've reached them. Or maybe the sum just didn't go up that much. Let's try 100 billion. Yeah, this is where technology can mislead you, because you might think, well, it's converging, and it's converging to about 21 point blah, 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 blah. But I know it's not, because I know something you don't know. You're about to know. I can get this to share my screen, or share the whiteboard. But look, the sum went up a little bit. I guess it's slowly calculating it. I'm going to do two things. I'm going to go back to first I'm going to kill Desmos with my batteries. And then I'm going to go back to the whiteboard. Then I'm going to pause the video while I plug up my computer and let you know a little secret about not only the harmonic series, but all harmonic series. All right, computer's plugged up. Desmos is shut down because it's taking a lot of computing power to calculate the partial sum of the 10 billionth partial sum, something crazy like that. But you got to be careful, because all technology has a breaking point, and so it's difficult to make conclusions about things for all real numbers when no technology can handle that. Well, for no technology. But what was I going to tell you about all harmonic series? Well, that's actually pretty simple. All harmonic series diverge. I know it seems like adding the reciprocals of the integers, positive integers, 1 plus 1/2 plus 1/3 plus 1/4. Each number I'm adding is getting closer and closer to 0. So it would seem that the sum would slowly settle down. But that's not actually the case. There's a variety of ways to prove the harmonic series diverges. One of them uses some calculus techniques, which we haven't gotten to yet. Well, the technique we've gotten to, we just haven't gotten to it in the context of the situation yet. But I'm gonna show you a proof that all harmonic series diverge, and it's made up of 2 parts. The first part is to prove that the harmonic series diverges. And how are we going to do that? Well, we're going to take advantage of a theorem that I don't think I've explicitly stated, but it makes sense, and I'll let you know what it is there. Actually, I wouldn't even have to say it. You would probably buy it because it just seems so right, because it is. All right, so let's start with the harmonic series. Sum from n equals 1 to infinity of 1 over n. So 1 plus 1/2, I spaced that out so much, plus 1/2 plus 1/3 plus 1/4 1/5. I'm going to take it out to 1/8. I remember how to do this correctly. I'm going to think out loud. We want this to be bigger than something that's going to diverge. So I need to pop these things to be greater than. I know. Okay. I mean, I can look up the proof, but I always hate just looking it up because I want to understand what's going on here. What we're going to do is we're going to show that this sum is greater than something else, and that something else will go to infinity. Well, if I'm bigger than you and you go to infinity, guess where I have to go? Infinity. So what are we going to make this bigger than? Well, we're going to leave the 1 alone, or we're going to leave the 1/2 alone. But now we're going to replace some of the add-ins with smaller values. Let's start with these 2. What's a number that's less than 1/3? How about 1/4? Now, if I left everything else alone, I just made the sum smaller. I replaced 1/3 with a smaller value. I'm going to leave the 1/4 alone. You're still struggling with why 1/3 is bigger than 1/4. Think about a pizza. Quit wasting your time comparing fractions, especially unit fractions. We're going to do the same thing, but this time we're going to do it with the next 4 terms. We're going to replace 3 of them with fractions that are smaller, making the sum lesser, meaning that the original sum is greater than what I'm writing. And the fractions I'm going to replace them all with is 1/8. 1/5 is greater than 1/8. 1/6 is greater than 1/8. 1/7 is greater than 1/8. 1/8 is equal. Now, I could repeat this again with the next 8 terms. So just pretend we have the next 8 terms. That says 8. The last of which would be plus 1/16. I would replace all 8 of those terms with 1/16 8 times. Again, all I'm doing is replacing some of the fractions with smaller values. Here. All I'm doing is replacing some of the fractions with smaller values, which means I'm decreasing the sum, which means the sum that I'm looking at right here is currently greater than all this over here. Well, what do we have over here? Let's see what all this equals. We have 1 plus 1/2 plus, what is 1/4 plus 1/4? 2/4, also known as 1/2, plus 4/8, which reduces to 1/2, plus, well, over here I have 1/16 8 times, so that makes 8/16, which reduces to 1/2. And because this is an infinite series, I can do this forever. I would take the next 8 terms and replace them all with 1/16. And I would take the next 32 terms and replace them all with 1 over 32. Each time I make those replacements, I'm actually making the sum smaller. Have. We now have 1 plus 1 plus 1 plus 1 plus 1. This approaches infinity. And the harmonic series is greater than that sum which approaches infinity. The only way you can be greater than infinity, so to speak, are infinity. Therefore, harmonic sequence diverges. Seems counterintuitive, but now not only does it diverge, I know how far I have to take it out to make it large as I want, because I've got a 1, I've got a half, and then I go out 2 more terms for the next half, 4 more terms for the next half, 8 more terms for the next half. I can count how many halves I want to go out the correct number of terms, and that would get me bigger than that. All right, so that's the first part of the proof that all harmonic series diverge, that harmonic series divergence. Namely, the sum of 1 over n from n equals 1 to infinity. Keep that in mind. If you ever see this series, that was just highlighted. If you ever see this series, you do not have to do anything. You simply have to say that it diverges, and if they're asking the reason, because you say it's harmonic series. The truth is, it's a harmonic series, because remember, any harmonic series is a series that looks like this. The reciprocal of basically something in slope-intercept form. A slope-intercept form would generate an arithmetic sequence. All right, so that's the first part of the proof, that the harmonic series diverges. So how do we prove that all harmonic series diverge based on that? Well, we actually have to split that into a couple parts. Well, we'll go ahead and call this just the proof part 2. And if you're wondering, why are you showing me proofs? This is calculus, because not everybody in this class is an engineer or physicist, and some people in here are actually going to take a lot more theoretical math classes. At some stage in upper level math, it is all proofs. So consider this an introduction, if you will. There we go. All right, so here comes proof part 2. This part of the proof, we are going to look at a generic harmonic sequence. So we'll say consider the following. Sum from n equals 1 to infinity of 1 over an plus b. And we're going to kind of play the same game that we played before, that we are going to find a series that has a lesser sum than this one and show that that series diverges to infinity. But we actually have to break this up in 2 different cases. The case is dependent upon whether or not the b is positive. So let's start with case 1, where the b is less than 0. If b is less than 0, then this implies that an plus b is less than an, which is really easy to see because we would just have to add an to both sides of this, and we would get that an plus b is less than an. But what does this imply? Well, if one number is less than another, then when you take their reciprocal, the order switches. For example, 2 is less than 3, but 1/2 is greater than 1/3. So if we reciprocate both sides, we have 1 over an plus b is greater than 1 over an. Got that fraction bigger than the fraction without the plus b. So that means that the sum from n equals 1 to infinity, 1 over an plus b, is greater than sum from n equals 1 to infinity of 1 over an. And it just dawned on me that I might actually have to break down the case of a being positive and negative. But since this is kind of a loosey-goosey, let's just assume that a is greater than 0. And I am confident that I could also come up with a proof in the case that a is negative. So we're just not going to worry about that right now. All right, so we have that sum. Actually, I'm not sure if that matters, but let's just pretend that it doesn't. We have the sum that we're looking at is greater than the sum from n equals 1 to infinity of 1 over a times n. But using something we haven't justified that we can do yet, you can factor a constant multiple out of a sum, just like you can factor a constant multiple out of an integral. So we can factor out 1 over a from the sum, and look what we get. Get the harmonic series. It diverges to infinity, so this approaches infinity. The 1 over a won't change that. Infinity is so big, you multiply by any fraction you want, it's still infinity. So what do we end up with? This sum, that's supposed to be a different color, this sum is greater than infinity, which is a recipe for divergence. Divergence. Now that was case 1 when the b was less than 0. So what about when the b is greater than 0? Well, it's kind of the same, but I have to do a little bit of finagling. What if the b is greater than 0? Then we have, I remember how I did this. This implies that an plus b greater than an. And reciprocating right now wouldn't be a good idea because that would put this less than this. And what we would say is that this sum is less than something that's infinite. But if you're less than infinity, it doesn't mean that you're infinite. So reciprocating right now is not a good idea. I do need to get the an by itself that could be removed from it and make sure that the direction that it's bounded is good. So the trick that I'm going to do is I'm going to multiply both sides of this inequality by -1. Now when you multiply by negative, it reverses the inequality. And now when we take the reciprocals, it reverses the inequality again. And so we have, and I hope I didn't paint myself into a corner here, the sum from n equals 1 to infinity, 1 over negative an minus b, is greater than the sum. Yeah, I just painted myself in a corner. I'll explain what it is. This sum, but we can factor out the negative 1 over a of n. And here's the corner I painted myself in. That's infinity. This might be negative. In fact, if we assume a is positive, then that is negative. So we've got this is greater than negative infinity. All right, so that kind of tank. I know another way to prove that all harmonic series diverge. The only problem is it uses a technique we haven't gotten to yet called the integral test. Basically, you can do an integral to see if the series diverges. So I knew I would get in trouble. Well, I figured I would get in trouble if I was careful with my positives and negatives. But unfortunately, this case blew up. I tried to improvise the proof video. So if I were turning this in as a real analysis assignment, I would lose points for making assumptions, which I should have made. But I can tell you that this part is true, unless I'm missing something. Well, no, this is assuming a is greater than 0. So that means that this is positive, that's positive, so it does positive infinity. So yeah, that part of the proof is true. That if everything is positive, we're okay. There's some other ways around what happens if the b is negative and if the a is negative, but I'm not going to waste any more of your time trying to put together a proof on the fly, since I didn't put it together well prior to the video. I can tell you this, though. This is what you really need to know. All harmonic series diverge. It's up here. All harmonic series diverge, particularly this one. All right, so yeah. Harmonic series are real easy to mess with. They diverge. You just got to recognize them.